Go ahead.
I just have questions about the lab.
That's fine.
For the assignment portion, the question 3,
What does question 3 ask?
write equations for hydrochloric acid and sodium hydroxide behaving as a Bronson acid and base respectively with water.
Okay, so that means, let me do share.
Yeah, I'm trying to
So,
write it out.
so you want to do hydrochloric acid as an acid
Right.
with water. Okay, so can you see what I'm writing here?
Mm-hmm.
Great. So if this is an acid, it's going to be a proton donor, right?
Mm-hmm.
So if it donates a proton, what does it become? And the answer is chloride ion.
Just chloride.
Mm-hmm.
So
And if
then
water is the base and gets a proton, what happens to it?
okay, becomes H3O.
Right, the hydronium ion. So this is water acting as a Bronsted-Lowry base with hydrochloric acid, which is an acid.
Okay, got that one then.
Now, how would water react with sodium hydroxide?
I had more trouble with that one.
Well, the trouble may be that it doesn't look like anything's happening. So here's what actually happens is this OH takes a proton from water. So what does water become when you take away an H plus?
OH.
OH minus.
Okay.
What happens to the OH when it gets a proton?
It becomes water.
It becomes water. So here, that's it, but it's hard to see.
Oh, okay.
That's it. So it's kind of tricky, isn't it?
Yeah. Okay. For number 5 of the lab,
Yes.
I'm not really sure because both are strong acids.
So the question is, why should it take fewer drops of sulfuric acid, right?
Yeah.
Okay, so let's take a look at the reactions. I'm not going to write the states out.
Okay.
So these are the two reactions that you wrote out in the previous question, number 4, correct?
Mm-hmm.
Okay, so I'm going to do something here that might not seem too normal, but I'm going to do it anyways, okay? So do you see what I've done there?
Yeah.
I doubled everything in the second equation. So the reason I did that is so that you could see that the NaOH in each of these reactions, there's 2 of them, correct?
Yeah.
How many of these does it take, HCl's, to react with these 2 NaOHs?
2.
Okay, and how many H2SO4s does it take to react with these 2 NaOHs?
Looks like 1.
Okay, so here it only takes 1. Here it takes 2. And the 0.1 m is the concentration. And we don't need to know what that means, but if they have the same concentration and you need 2 of these to neutralize the base, and you only need 1 of these, doesn't it stand to reason that you're going to need twice the volume of that to make it happen?
Yeah.
So imagine, if you will, so another way to think about this is imagine you're transferring water from one place to another. And here, this has 2 hydrogens that'll react. You with me?
Yeah.
This only has one. Are you with me?
Mhm.
So this is like having a half a cup container, and this is like having a full cup container. This is twice as much as that, right?
Yeah.
So how many, so can you see that this is going to take twice as much to shuffle around water wise as far as that goes? Another way to look at it is this way. Eight drops, and it doesn't really matter what we're looking at here, but I'm going to put in 8 drops of this, you have HCl, HCl, and HCl. 3 of them, okay?
Okay.
So these are the same concentration. So there's 3 of them. Okay? Are you with me there?
Mhm.
And actually, I'm going to make it 4.
Okay.
So how much base will this react with?
How much space?
Base. How much sodium hydroxide will this react with?
Well, 1-to-1 ratio.
Yeah, so 4 of them, right?
Yeah.
How many will this react with?
4.
One of them reacts with 2. So how many will 4 of these react with?
Oh, 8.
8. Now, if we have NaOH, so here's 2 separate containers of NaOH, okay? And here you have 4 of these in each. So this is the situation where you put 6 drops in each container. You with me?
Mhm.
Then you add this stuff in. How much of this stuff do we have to add to make this neutralized?
3
And you
drops.
would want 4 HCl's, right?
Mhm.
And we said that that would be 8 drops.
Yeah.
How many H2SO4s would you want?
2 drops.
2.
Okay.
Because each one of them comes with 2 hydrogens, so it can neutralize 2 of these. How many drops would that be?
You said 2 drops.
It'd be, well, if 4 of these is 8 drops, then 2 would be 4 drops, right?
Yeah.
So here you can see that it would take fewer drops of sulfuric acid to neutralize the sodium hydroxide because it is diprotic,
So because it has more hydrogens, more
right?
protein.
Exactly. And phosphoric acid, which has 3 hydrogens, would take even less.
Okay. So the key is the hydrogens.
Yep. The key is the number of hydrogens.
Okay.
What else can I help you with?
The next one, number 6.
What does that one ask?
For the reaction of vinegar in the penny, you should have noticed very tiny bubbles, blah, blah, blah. That's hydrogen gas. The acetic acid in vinegar is reacting with zinc to form zinc acetate and hydrogen gas. Write a balanced equation, reaction, and sign oxidation numbers, blah, blah, blah.
Okay, so you should have this. Here's the vinegar, here's the acetic acid in vinegar.
Okay.
It's
So,
reacting with zinc. Here's the zinc to make zinc acetate. Whoops, that hydrogen shouldn't be there.
that's, okay.
And hydrogen gas. So did you notice little bubbles forming at the edge of your penny?
Yeah,
That's hydrogen gas. It's not very vigorous, is it?
no.
No, if you used a stronger acid like hydrochloric acid, it would bubble furiously.
Oh,
But we wanted to make this safe, so we just used vinegar, which if you get in your eye will hurt, but it's not going to damage your eye permanently.
so when I was writing out this equation, I thought the product with the zinc acetate, there would be 2 because of the charge of the zinc.
Yep,
Is that not right? Oh,
that is right. So how many of these do you need?
we need 2 over there.
Okay, so now it's balanced.
Okay.
Now
Okay.
let's assign oxidation numbers. So the first rule you want to use is if you see a neutral element, it's 0. Do you see
Right.
any of those?
Zinc,
Any others?
hydrogen.
Correct. Okay, so those are zeros. And then our next rule is if you have any monoatomic ions, the oxidation number is equal to the charge. Do you see any monoatomic ions?
Well, would the zinc and zinc acetate be one?
Yep. So the zinc is a +2. Are there any other monoatomic ions?
No.
Okay, so there's this guy here,
Mm, yeah.
right?
Yeah.
CH3COO minus, and there's this guy here. So for these, what do we assign first?
Mm, oxygen? No,
No,
hydrogen.
hydrogen.
That's +1.
+1 each on these and +1 each and +1 over here, right?
Yeah.
Now what do we do?
Oxygen, which is -2.
Okay, -2 here, -2 here, -2, -2 here. What do all of these add up to? Now remember, there's 3 hydrogens here.
Oh, so that's neutral.
So that adds up to 0. So that means the oxidation numbers on the carbons, we're just going to write as zeros.
Okay. So we can do that.
We can do that. That's fine.
Okay.
Okay, so I'm going to put that 0, +1, 0, -2, -2, +1. +1, or 0, +1, 0, -2, -2. So look at this carbon. Did it change?
No.
How about these hydrogens? Did they change?
No.
No. How about this carbon?
No.
No. How about this oxygen?
Nope.
Nope. How about this one?
Nope.
How about this hydrogen? Well, this hydrogen must be these two, right?
Right.
Did it change?
Yeah, it decreased.
Okay. How about the zinc? Did it change?
Yes, it increased.
Okay, so I like to start with decrease because decrease means
Reduced,
reduced means,
gain, oxidizing.
right. I like to go ahead and write rig.
Yeah.
So it's the oxidizing agent. And remember how we talked about acids in general are oxidizing agents?
Yeah.
Well, this is an acid and it's an oxidizing agent. Now, zinc, you may remember we talked about metals like sodium. They tend to be reducing agents, right?
Mhm.
And here we have zinc, which is a metal like sodium, and it gets oxidized, which is oil, loses electrons, and is a reducing agent. So the reason metals tend to be reducing agents is because they get oxidized, which means they lose electrons. And we know that metals tend to lose electrons to become ions, cations.
Mhm.
Okay. So that's how you do this one.
Okay. I think that's all.
Okay. Do you want to, since I have your attention, do you want to finish off those problems from chapter 3?
Do you want to? Sure, but do you want to just go over a bunch of practice problems?
Well, that's what this is. Well, we can do other practice problems if you want. Do you have any in mind?
Um, I guess just really drilling in net ionic equations for all the different type of reactions.
Let me see. I don't think this one made it into the recording, number 74.
Okay,
So that's the net ionic.
right.
We did 78, but that didn't make it into the recording, but we did do a net ionic for that one.
Yeah.
82 is a net ionic. 86 is a net ionic. So there's a few net ionics in here. So let's focus on the net ionic ones, okay?
Okay.
And so these will make it into the next recording. People can just look at what they want. Okay, so identify and name the water insoluble product in each reaction and write the net ionic. So for this first one, I'm just going to copy the two reactants. And it says name the water insoluble product, which means, okay, it's a precipitation reaction, right?
Yeah.
And we know that the product is going to be an ionic compound. And so looking at the two products here, it has to be the copper sulfide, copper 2 sulfide.
Yes.
So that's got to be the solid. And we know hydrochloric acid is aqueous.
Mm-hmm.
Okay, for the net ionic, we know that it's a copper 2 ion that's aqueous. We know it's 2 chloride ions that are aqueous. Since this is a weak acid, it's H2S aqueous. And we have copper 2 sulfide, solid. And then we have 2 H pluses that are aqueous and 2 chlorides that are aqueous. And this is an acid like H2S. But the reason we are separating the protons from the anion for the HCl is because it's a strong acid.
That's right.
So this one's strong, this one's weak, and look at how we treat weak acids and look at how we treat strong ones.
Yeah, they disassociate.
Okay. Now, if we look at what's identical on both sides, it's the 2 chlorides. These are spectators, right?
Mm-hmm.
So what remains is the net. The copper 2 ions that are aqueous, the H2S that is aqueous, the copper 2 sulfide that is a solid, and the 2 H pluses that are aqueous. And this copper is getting reduced.
Right.
And so this is an acid that's not really acting like an oxidizing agent.
Right.
Okay. Now, what do we call this? We call this copper 2 sulfide. Now, why do we have to write the 2 there?
Because it has a positive 2 charge.
Well, I was going to say because it's not 1A, it's not 2A, it's not 3A, it's not zinc, it's not silver. That's why we have to write the charge.
Okay.
So here's your answer. Identify and name the water insoluble product and write the net ionic equation. So here we've done both. Let's look at C. So for C, I'm going to do the same thing. Calcium plus 2 ion, aqueous. 2 chlorides that are aqueous. How do we know that these are 2 ions and not elemental chlorine? Because this is an elemental chlorine Cl2.
Yeah,
How do we know that's not elemental chlorine?
I don't know.
The answer is simple, simpler than you may think. Right next to another atom, which means it's part of a compound, which means it's not a pure element by itself.
Right.
Okay. It would have to be written like this to be elemental chlorine.
Right.
So the fact that there's no plus sign between those means it's part of a compound. Okay, so there are two chloride ions, two potassium ions, one carbonate ion, and then I have two potassium ions. I have two chloride ions, and I have one calcium carbonate, which is a solid. And I know it's a solid because carbonates are not water soluble unless they're combined with things like sodium or ammonium. So if we look at the before and after and see what's identical, which are the two chlorides and the two potassiums, and they get removed, we then get calcium 2 ion plus carbonate ion makes calcium carbonate solid, and this is called calcium carbonate. Now, why do I not have to write calcium 2 carbonate when it indeed is a calcium 2 ion?
Because it's in group 2.
Because it's in group 2. They're all plus 2. And so there we go. There's your net. And there's the name of the product. So how about C? Why don't you tell me when you're ready for C? And we'll look and see if we get the same answer.
Okay.
How's the weather in Crescent City?
Sunny right now.
We're a little overcast. I'd say patchy clouds.
Yeah.
Are you ready?
Yeah.
Okay, so these are all the ions. The sodium ions are the same on both sides. The nitrate ions are the same on both sides. So the net is going to be a silver ion that is aqueous, reacting with an iodide ion that is aqueous to make silver iodide solid, and the name is silver iodide. How come we don't have to put silver 1?
Because it's part of the given ones.
Because it's part of 1A, 2A, 3A, silver or zinc. So it's the silver part.
Yeah.
Okay, so there you go. Now this one, we talked about this one. Remember that nonmetals tend to be oxidizing agents, O2 and Cl2. So those two we'd expect to be oxidizing agents. Metals tend to be reducing agents. And I believe we said something like this. If you look at the metal, what's most likely to happen to this metal is that it will turn into a sodium +1 ion, which means its oxidation number goes from 0 to +1, which is an increase, which means it's oxidized, which means it's oiled, loses electrons, and is a reducing agent. So because most metals like to become cations, they are reducing agents. Whereas when you look at Cl2, they usually become chloride ions. So they go from a 0 to a -1, which means they go down, they're reduced, they're rigged, they gain electrons, and they're oxidizing agents. So because nonmetals become anions and gain electrons, they cause oxidation. So they're oxidizing agents. And in general, acids are oxidizing agents. And a lot of the times, the reason that acids are oxidizing agents is because you have these H pluses turn into H2s. And so here you go from a +1 to a 0, which means that's reduced, rigged, gains electrons, and is therefore an oxidizing agent. And then we also talked about these guys here. Usually these polyatomic cations, or back it up, those polyatomic anions with oxygen, usually because they have oxygen, they're oxidizing agents. Okay?
Okay.
Okay, so this one, they don't ask for a net, but we're going to do that. Write the overall reaction and indicate the states. So ammonium sulfide, it says it's aqueous. So the question is that going to be dissolved in the water? And the answer is yes, because of the ammonium.
Mm-hmm.
Is the mercury compound going to be dissolved in the water? And the answer is yes, because of the nitrate. Now, is the mercury with the sulfur going to be dissolved in the water? And the answer is no. There is no rule that says that they will be soluble. And in fact, if you look at the non-soluble rules, they do say that sulfides are not soluble.
Yeah.
But the fact that it's not part of the soluble rules is enough for us to say it's going to be a solid. Okay?
Okay.
So that's kind of like a hint. If you want to put the solubility rules on your card, put the ones that do dissolve on your card and not the ones that don't dissolve. Because if you have the ones that do dissolve and what you're looking at doesn't fit that, then you say, hey, it doesn't dissolve, or it's a precipitate. Does that make sense?
Yes. What do you recommend for the exceptions?
It's easy enough to write the exceptions down, I think.
And they're all pretty close to the same.
They are, but you might want to go ahead and put that down too.
Okay.
You know, for chlorides versus sulfates, they're not quite the same, right?
No.
So you might want to write those down. All right. Now here we have this ammonium nitrate. And because it's got ammonium in it, that's enough to say it's going to be soluble. And with a nitrate on it, that just confirms it.
Right.
Now to balance this, we have two ammoniums on the left and one on the right. So I'm going to put a 2 in front of the ammonium nitrate. I've got one sulfur on the left and one on the right, one mercury on the left and one on the right. 2 nitrates on the left and 2 on the right, so we're balanced, okay?
Mhm.
Now, we know that nitrate is always soluble, right?
Mhm.
So we know that's not going to be in the net. Okay. We know ammonium is always soluble, right?
Mhm.
So it's not going to be in the net. So I'm going to go straight to the net and say, well, the sulfur has to be in there because I don't see any sulfur aqueous on this side. The mercury has to be in there because I don't see any aqueous mercury on this side. And here is the net ionic reaction. Now, a student asked me the other day, does it matter that we put the cation first and the anion second, or can we just write them in any order we want? And the answer is when they're aqueous, it doesn't matter. The order does not matter. But in a compound, the order does matter. Okay, so what I have here is perfectly fine. But if you preferred to put the mercury first and the sulfur second, that's also fine. Okay, so that's the net. They also ask us, name each compound. So what's the name of the first compound? Ammonium what?
Sulfide.
Good. A lot of people confuse sulfide and sulfate, nitride, nitrate, and those things, right?
Mm-hmm.
How about this one?
Mercury nitrate. I don't know.
Close. Mercury 2. Why does it require a number?
Because it's not one of the given.
How about we say that better?
I don't know.
Because it's not in 1A, 2A, 3A. It's not silver. It's not zinc. If you say that again and again and again, then it starts to sink in. When you say because it's not one of the givens, you just kind of lose it. So why do we put the charge on that one?
Because it's not in group 1A, 2A, not zinc or silver,
And it's not in
or
3A.
3A.
Don't give me that look.
Okay.
Trying to help you out here. Now, what do we call this guy here at the end?
Mercury sulfide.
No.
Mercury 2.
Oh, why do you want to put a 2 there?
Because it has a +2 charge.
And
It is not in group 1A, 2A, 3A. It's not zinc. It's not silver.
there you go. That's the question you should be asking yourself every time you see a cation. Do I need to write the charge?
Okay.
Okay, so that's B. And then C says, what type of reaction is this?
Precipitate.
Precipitation. And I am perfectly fine if you guys want to abbreviate and write PPT.
Okay.
Precipitation. So PPT. Okay. So this one is not a ionic. So here's a net ionic one. So aqueous lead 2 nitrate and aqueous potassium hydroxide. So lead 2 nitrate. Now see, here's one where they have to tell us the charge
Right.
because it's not in 1A, 2A, 3A. It's not silver, it's not zinc. Nitrates are a +1 charge.
Mhm.
So this has to be the formula, 2 to 1.
That's what I got.
Potassium hydroxide. We know potassium's a +1 because it's in group 1A. Hydroxide we memorize as being a -1.
Mhm.
So there's one of each. Now, what type of reaction is this? It looks to me like it's not an acid base. We certainly have a base here, but this is not an acid. Doesn't look like a redox because I don't have a pure element anywhere. Doesn't look like a gas forming because I'm looking for sulfite or carbonate for a gas forming.
Right.
And so this must be one of those precipitation reactions. So
Yeah.
we know potassium is always soluble, right?
Yeah.
And we know that nitrate's always soluble.
So that's
So
gonna
the
be
solid must form between lead and hydroxide. So what would be the formula if this is a lead 2 and the hydroxide is a -1?
PbOH2
Good.
solid.
And of course, if we're going to have two OHs here, we need to have a 2 in front of the KOH, right?
Mhm.
Isn't there such a thing as a KOH campground?
KOA.
Right, KOA. Okay. And here, what's left over are the 2 potassiums and the 2 nitrates. Oops. So I'm going to write it out as KNO3, but a 2 in front of that.
Okay.
So here's an overall balanced equation. Now, what's the net ionic going to be? Well, we know that the nitrates are always soluble, so I'm going to leave those out. We know that the potassiums are always soluble, so I'm going to leave those out. And so I'm kind of showing you a shortcut for how to get to the net ionic on this is, hey, leave the always soluble ions out and you're going to get your net. So this is
2OH.
this is the overall. This is the net. And yeah, we do need a 2 here because of that. So that's A. Any questions about A?
No.
Okay, then let's look at B. So tell me exactly what I should write.
Copper nitrate 2. So parentheses nitrate and then a 2.
And then,
Aqueous.
okay.
This is a nitrate. And then NaCO3. Aqueous.
Yeah.
I think so. No. Na2
Yes. Why?
because carbonate has a 2- charge.
That's right. What's the state of this stuff?
Aqueous.
Not only because the statement is that it's aqueous, but because it's got sodium in it, right?
Mm-hmm.
Okay. So this looks like another precipitation reaction. There is the carbonate there, which makes you think maybe it's a gas forming. However, we need an acid over here for it to be a gas forming. And this is not an acid. Fair enough?
Yeah. So we're gonna have copper 2 carbonate as a solid, right?
Yes. And what's the other product?
Sodium nitrate.
How many?
Just one of each.
Yes, one of each in the formula. And how many total formulas?
2. So you put
Yes,
2 in front.
because we have 2 sodiums and 2 nitrates. What's that's the overall. What's the net look like?
Wait, is the solid copper 2 carbonate or is it just copper carbonate?
Well, carbonates are generally not soluble, so it's going to be a solid.
So, but is there 2 coppers?
No, because it's a copper 2. Copper
Okay,
2 is the charge, not how many.
yes, I remember, but I was
So
thinking,
carbonates are -2, coppers are +2 in this equation.
okay,
It would
so
be-
they balance, that part balances them
Yeah,
out. Okay, okay,
yeah, you need to really recognize that carbonate is a -2.
2 9.
Okay, so what's the net gonna look like?
2 Na pluses.
Nope. Are there gonna be any nitrates in our net?
No,
Because they're always soluble.
right.
Are there gonna be any sodiums in our net?
Oh, no.
Because they're always soluble. So what's gonna be in our net? The copper and the carbonate.
Okay.
Now, if we do it the long way, which I'm gonna do now, the long way is to take a look at the copper 2 nitrate and write out copper 2 plus 2 nitrates. And so that's the copper 2 nitrate. The sodium carbonate would be 2 sodium ions and 1 carbonate ion. And then the copper 2 carbonate would be written exactly the same because we always bring solids, liquids, and gases right down as they are written.
Mhm.
Okay, so this, we don't change one bit because it's a solid. And here, because this is aqueous, we have 2 sodium ions that are aqueous and 2 nitrate ions that are aqueous. And I'm running out of room here. The nitrate is the same on both sides, 2, and they're both aqueous. The sodiums are the same on both sides. So we just write down what remains, which is the copper ion, that's aqueous, the carbonate ion that is aqueous, and the copper 2 carbonate solid. Okay, so you kind of go 1, 1, 2, and then get there. Okay, so that's kind of like the long way to do it. And that's the way you want to do it at first until you get used to it. Okay. So here they're looking at which ones of these are strong acids, which ones are weak acids, or actually they're looking at which ones are going to dissolve really well and make ions. So here for A, if we look at copper carbonate, copper, this should be called copper 2 carbonate, copper 2 hydroxide, copper 2 chloride, and copper 2 oxide. Which ones will dissolve in water? Well, this one's not soluble in water because the carbonate. How about this one? This one's not soluble water because the hydroxide.
Mm.
Now, if we aren't writing those rules down about what doesn't dissolve, for these we'd be saying not soluble because it doesn't have sodium, potassium, or ammonium or something like that in there with the carbonate, right?
Yeah.
And the same thing here because it doesn't have sodium and so forth and so on. This one is soluble because halides are soluble unless with silver or lead. Those are the 2 major ones.
Okay.
And this one is not soluble because oxides tend to be not soluble unless you have sodium oxide or something like that. So this is the only one that's soluble, and it's because of the chloride ion. For B, HCl is soluble because it's a strong acid. H2C2O4 is not very soluble because that's a weak acid. You just have to memorize that that's a weak acid. It's not one of the ones I asked you to memorize, but you could look it up in the book. H3PO4 is not very soluble, or so it's a weak acid. And I'm actually going to put weak acid. And I'm going to put strong. And the last one is H2SO4. What do we know about that? Strong or weak?
Weak.
Strong.
What was I thinking of?
Maybe H3PO4 or
Okay.
carbonic acid.
Yeah.
These
So I
are
have
the 3 strong ones I wanted you to memorize.
only 3 because I have like 6 on my list.
What else do you have? Do you have perchlorate, perchloric acid,
Yeah.
chloric acid?
Hydrochloric, hydrobromic, hydroiodic.
Yeah, but those are all like HCl,
Okay.
so they're pretty similar. However, HF is not. HF is actually weak. So which one of these would conduct electricity well? And the answer is the strong acids and the things that would dissolve. The ones in the squares would conduct electricity well in aqueous solutions. And the reason is because they produce ions in aqueous solution. Okay? Okay, this is going to be the last one we do. Write net ionic reactions for the following. Reaction of acetic acid, a weak acid, and strontium hydroxide aqueous. So this is one of those weird ones where apparently this hydroxide is soluble because it's with strontium. Okay, now I'm going to go ahead and write out the reaction itself. Here we have 1 proton, here we have 2 hydroxides. So 1 and 2 is not what we want 2 and 2. So I'm going to put a 2 here. And now we have 2 H pluses and 2 hydroxides, which means 2 waters. And water is a liquid.
Mm-hmm.
We're also going to have strontium and acetate left over. And that's going to be aqueous because of the acetate. So there's your overall reaction. So what are we going to bring down for sure? The H2O, because it's a liquid. Okay?
Right.
Now, for the aqueous things, if it's a weak acid, you also bring it down. Because weak acids do not come apart very well. So we can't write them out as ions like we can strong acids. Strong acids, they come apart, so you write the ions. Weak acids, they don't.
Do we include the H on the end of that?
Oh, yeah. Absolutely, because it sticks together. In fact, this is the way the molecule looks like in water. And there's the hydrogen on it right there.
Yeah.
Okay. And that stays on for the most part in water. Like maybe 1 in 100,000 comes off. That's it.
Okay.
1 out of 100,000. So if 99,999 look like this, and one of them looks like this, So 99,999 and 1. What drawing should we draw to represent it? Should we draw this one or this one?
The top.
The top one. So if we do the top one, then we write the formula out as is. We don't write two separate things. So that's what you do for weak acids.
Okay.
Strong acids, it's the reverse. It's like 99,999 and 1. So you write it out this way, two separate ions, okay? All right. Now this one, they say it's aqueous, so strontium +2. How do you know it's a +2 charge?
Because of the hydroxide has 2 of them.
Okay, and they're each a -1. What's another reason why we know it's a +2?
It's not in group 2A, is it? Oh, it is.
Because it's in group 2A.
Yeah.
So here's the rest. So what is identical on both sides?
Strontium.
That's it. So the net is not really much shorter than the total, is it?
Right. And again, we're not counting acetic acid in this because it's a weak acid.
That's right. It stays together because it's a weak acid. Whereas, this is not a question that was asked, but what would we write if we had this reacting instead? So this is a good contrast between a weak acid and a strong acid. So here's a strong acid, 2 hydrogens, 2 hydroxides. How many waters?
2.
1 strontium left over,
Mhm.
2 chlorides left over, and because of the Cl, it's aqueous.
Mhm.
Okay, so here, if we want to get the net, so this is the net up here, we'd write 2 H pluses
Mhm.
plus 2 chlorides plus a strontium plus 2 hydroxides gives you 2 H2Os, 1 strontium, and 2 chlorides. So what's identical on both sides? The chlorides,
And strontium.
the strontiums. So you would have 2 H pluses plus 2 hydroxides gives you 2 H2Os. So you see those nets are quite different between a strong acid and a weak acid.
Yeah.
So strong acid, you write the ions out for the acid. Weak acid, you don't write the ions out. Okay?
Okay.
All right, so we're ready for B. Zinc and hydrochloric acid to form zinc 2 chloride. Now, this is an interesting one because they actually use the 2 and you don't need to.
Right.
But we're not gonna, we're not gonna look a gift horse in the mouth, right? We're gonna go ahead and write that down. Okay, is it balanced?
No. We need a 2 in front of HCl.
Excellent. Now what do you want to do?
We're going to bring down the Z
Absolutely, bring the zinc down.
because it's a solid. And then the H2 on the product side.
Absolutely, because it's a gas. And this HCl, what does it look like in solution? Does it stay together usually, or does it come apart?
H plus and Cl minus.
So I'm going to go write H plus and Cl minus on the bottom, 2 and 2, right?
Yeah.
What about the zinc chloride?
Zinc 2 plus.
And 2 chlorides, right?
Yeah.
And the chlorides are going to be exactly the same, right?
Mm-hmm.
So that means we're going to have the 2 H pluses here. And we're going to have the zinc here. And if we've done this right, we should have 1 zinc on the left, 1 on the right. 2 hydrogens on the left, 2 on the right. Overall on the left, you've got a 0 charge on the zinc, +1 on the hydrogen, but there's 2 of them, so that's a +2 on the left. On the right, you've got a +2 on the zinc and no charge on the H2, so you've got a +2 on the right. Charges match, atoms match, done. So there's your net.
Why is the zinc aqueous on the product side?
Well, because of the chloride. Chlorides are soluble unless they're mixed with like lead or silver. Those are the 2 big exceptions.
So when we write the net, we take that into consideration.
Oh, absolutely. So if we kind of do this the long way, we would do this.
Mm-hmm.
The zinc stays the same. 2 H pluses that are aqueous,
Mm-hmm.
plus 2 chlorides that are aqueous because it's a strong acid. Because zinc chloride has chloride in it, it's aqueous. So you have a zinc ion that's aqueous, plus 2 chlorides that are aqueous. And then for H2, because it's a gas, you don't separate it into ions. So can you see what's identical on both sides?
Yeah. All right.
So they are the spectator ions. And you can see that the zinc ends up in it, the hydrogen ends up in it, I should say protons. The zinc ion ends up in it, and the hydrogen gas ends up in it. Okay?
Okay.
All righty. So let me did I record this one or did I screw this one up too?
You recorded it.
Oh yeah, I see the little thing. I don't know why, but when I mess around with changing my share screen, the little dot that blinks that says I'm recording moves from one place to the other. I need a larger monitor.
Yeah.
Okay. All right. So does that help you out a bit?
Yeah.
Okay, excellent.
Thank
Now it
you.
must be time to go do some CrossFit training, right?
No, I haven't been doing that lately.
Oh, I just noticed the sweatshirt.
I know. I don't have time anymore.
You mean with chemistry and a young un and a husband, you don't have time for anything else? Can't
No.
imagine why.
I know.
But I'm sure it's all worth it, right?
Mm-hmm.
Okay, cool. Well, thanks for dropping in. I
Thanks.
appreciate it when people do that.
All right. Bye.
Bye-bye.